Hello, Math Study students, and welcome to your online lesson. Today we'll be talking about solving unknown functions or unfamiliar functions, so not linear equations or quadratic equations, but something that we haven't studied in depth. And we're going to be using technology to solve those unfamiliar functions. We'll know we're successful when we can efficiently solve unfamiliar functions with technology. So to start with, I've got three little sketches up here, each containing a pair of graphs. One of the graphs is a parabola, or a graph of a quadratic, and the other is a linear function, or a line. In the first example, I've labeled it as cutting, where you can see that the line is crossing right through the middle of that parabola. And the next one we're touching, where they're just sort of grazing. And the last one is labeled as missing. Well, my question is, how many points of intersection do each of these have? Well, in the first one, the one labeled cutting, you can see that it crosses not once, but twice. So there's 2 points of intersection. On the next one, the line is almost like a tangent. In fact, it is, which means it's crossing exactly 1 point, or intersecting at 1 point. And so the last one, we can see they're missing. They're not intersecting at all. So that would be 0 points of intersection. Well, why is this important for today's lesson? Well, each point of intersection represents a solution, or an ordered pair, or an answer that these two equations would have in common. So a point that would make our line be true, or the equation of the line be true, as well as the equation of our parabola. And so there would be two solutions for this first one, because there's two places where they cross, two x and y values. And then here we can see there's one equation, or one solution, I'm sorry, that would work for both the parabolic equation, the quadratic, as well as the line. And then here we have no places crossing, so there are 0 solutions. All right, and we'll need that information as we get to our examples here in just a moment. For our first example, I have us solving the following linear equation. And I can't even really use the word function here because it doesn't have an input and an output. This is just a basic algebra problem where we're supposed to find x. And we can do this without technology of any kind. So the first thing we'd want to do is to get x alone, we ask ourselves what's happening to x. And we have a -5 or a -5. So we're going to undo that by adding 5 to both sides. So those would cancel out. We'd end up with 8 on the left-hand side of our equation. We bring down the equal sign and our 2x. Now the last step to get x all alone is we divide by 2. So x is equal to, and 8 divided by 2 is 4. So there is our solution. Of course, we can check the solution by plugging it into the original equation. 3 is equal to 2 times 4. Again, 4 replacing our original x minus 5. And again, I'm just basing that off this original equation. 3 is equal to 2 times x, which we now know is 4, minus 5. So 3 is equal to 2 times 4 is 8, minus 5. And 8 minus 5 does, in fact, equal 3. So it's a total true statement. We've checked it. We've solved it. And we didn't need any technology of any kind. So the reason I started with this problem is I wanted to take a problem that we already were familiar with, that we knew how to solve, and that we could use the technology to confirm our answer so that we can then apply that to more complicated things. So the technique that we're going to do here is we're going to break apart this single equation into two separate functions, or two separate equations. So I'm going to start with the left-hand side of the equation. And what did we have on the left-hand side of the equation? We had a 3. I want to make a new equation with y equals 3. Well, what does that mean if I say y equals 3? If you remember back to our lesson on asymptotes, that would mean that's a horizontal line. This is an equation of a line, and the equation of lines can often be put in the form of y equals mx plus b. But you'll notice there's no x involved here. It's just y equals 3, which means that our m, or our slope, must have been 0 to cancel out the x altogether. And if there's no slope, what kind of line is that? It's a horizontal line. So we have a horizontal line with a y-intercept of 3. So if I go up 3 little spaces here, I can draw a nice horizontal line, and that would be my equation of y equals 3. All right. Now what I'm going to do is I'm going to take the right-hand side of this equation, 2x minus 5, and I'm going to make up a little function for that as well. Y equals 2x minus 5. So I just put a y equals in front of it. And you'll notice that's also in the form of y equals mx plus b, where we have our m, or our slope, and then we have our y-intercept, or our b value. So our y-intercept's at -5, so 1, 2, 3, 4, 5. That's my y-intercept there. My slope is 2, or rise 2, run 1. So I go up 2 over 1, up 2 over 1, something like that. So I'll end up with that little sketch there. And they cross at one point, meaning there is one answer to where these two graphs intersect. So there's one answer to where the right-hand side is equal to the left-hand side. Now what we're going to do is I'm going to get out my calculator and I'm going to show you to use technology to figure out exactly where those two things cross. And hopefully we'll make some connections. So on my calculator, I'm going to take my red equation, which was y equals 3, and I'm going to go to my y equals on the calculator, and I'll clear it out here. I already had them in, but I'm going to type y equals 3. So I just have what the y equals. And then for my second y, or my y sub 2, I'm going to type my green equation, y is equal to 2x minus 5. So 2x minus 5. Where did these come from? Well, again, the 3 was just the left-hand side of my original equation, and the 2x minus 5 was the right-hand side. So in one y, I'm putting the left-hand side of my equation, and in the second y, I'm putting the right-hand side of my equation. And now I'm going to hit graph. And you can see that looks very much like my sketch. And once again, there is apparently one point where they're intersecting, or one answer to where these two, that would make these both true. So how do we find where that value is? I'm going to press second trace, which we've done many times in this course. And we've done it for all the first four options, for 0, minimum, maximum, many times, and even value a little bit. But intersect is where we're going to go this time, which is choice 5. I want to find where these lines intersect. So after pressing choice 5, it asks me a question. It says first curve, question mark. So curve, there's really no curves anywhere happening on the screen. And what they mean by curve is just first function, first graph. And you'll notice that the cursor that's flashing right now is on my horizontal line, my y equals 3. And that was the first function that I typed in. So all I'm going to do is just say yes by pressing enter. Now you'll notice that my cursor jumped down to the y-intercept still, but of my slanted line, or the one that was green in my sketch right there. And so it jumped to my second function, and it's saying second curve, and it just wants me to confirm that that is my second function. Well, I only typed in two equations, y1, which was 3, and y2, which was 2x minus 5. So it's automatically going to be the first and second one. So I just hit enter both times, and then it asks for a guess, and I hit enter again. You will now notice that it is giving me an x value of 4. Well, where did we see that already? Well, when we did it by hand, we got an x value of 4. So you might be saying, why did we go through all that work on the technology just to find the answer that we could have done using basic algebra skills? Well, again, if we know it works with the basic problem, then we can apply this to a much more advanced problem, which we'll do in a moment. Before that, I just want to repeat the steps that we did here. So we pressed second trace. Actually, before that, we went to y equals. I typed in on the left-hand side of my equation, which was a 3. I went to y2, and that was the right-hand side of my equation, which was 2x minus 5. Then I graphed it. I hit second trace. I want to find out where those two equations intersect, so I hit 5. First curve, enter. Second curve, enter. Guess. In this case, it doesn't matter because there's only one point where they intersect. I hit enter again, and then again, I see the value that will solve this, x equals 4. All right, let's try it again now with a much more complicated example. So for this one, you can see we have a lot more going on with the equation. It's not a quadratic because we actually have x to the third power. And so it's not something that we've solved by hand using any of our factoring techniques or algebraic solving techniques. But you will notice there's a left-hand side of the equation, and there is a right-hand side of the equation. Right-hand side is just linear, x minus 1. The left-hand side is technically a cubic, but again, it's got that extra powers. But we can use our technique that we just used on the last example to solve this. So what are we going to do? We're going to go to y equals, and I'm going to put the left-hand side of my equation in first. So that was x to the third power minus 5x. And then I'm going to go to my second equation, clear out what I had in, and just type x minus 1. So once again, I've put the left-hand side of the equation for my first y and the right-hand side of my equation for the second y. Now I'm going to hit the graph key. Much more complicated here. I have this left-hand side, which has this sort of curve shape, which is typical of when you have an x to the third power. And then the right-hand side was my second equation, which is this just line. And we knew that was going to be a line because it's just x minus 1. You will notice there are 1, 2, 3 spots where they intersect. So I'm going to have 3 solutions to this problem, 3 values that will make it true. So I'm going to press second trace just like we had done. I'm doing intersect. First curve, I just hit enter. It's automatically going to the first one I put in. Second curve, I just hit enter. Now the guess. Now this time it's more important because there's 3 different spots. So I'm just going to move my cursor until I get the little flashing spot very close to the first intersection. And I'm just going to hit enter. And I get a value of negative 2.5, and I'm going to round to 3. So x is approximately 2.53. I'm not concerned about my y here. I'm just trying to find values of x that will make this true. All right, and now I'm going to repeat that again, but this time I'm going to be looking for the second intersection here with the red arrow. And so I'm going to press second trace. And I want intersect, so I press choice 5. First curve, enter. Second curve, enter. Now the guess, I need to move my cursor so that I'm closer to the second one. And I'm getting an x value this time of 0.167, rounded to 3 significant figures. And then I'm going to do this one last time. Second trace, intersect, first curve, enter, second curve, enter. And my guess, I'm going to move my cursor closest to the third intersection point. It doesn't have to be right on it, it just has to be closer to that intersection than any of the other 2. And I hit enter, and it gives me another intersection value of x equals 2.36. Now, what does this mean? Well, we can check these values by plugging them in. Now, you'll notice I rounded all of these values, so I might be off by like 100th or something like that. But I'm going to take my, let's just pick one at random. We'll do this last one here that I had. So I'm going to plug it in everywhere I had an x in my function. So in my function, I had an x being cubed minus 5 times my x, x, and that was equal to my x minus 1. All right, and so I'm going to plug in 2.36 to the third power minus 5 times 2.36. And I'm going to see what that is on my calculator, and it should be equal to 2.36 minus 1. Well, I can do 2.36 minus 1 without a calculator. I have 2.36, I take away 1, now I should have 1.36. Well, that means that all of this right here should be approximately, or very close to, again, because we are dealing with rounded values, but it should be about 1.36. So let's check it out on the calculator. I'm just going to use the regular entry screen. So second quit to get out of where my graph is. Now I take 2.36, and I'm going to take it to the third power, and then I'm going to minus 5 times 2.36. And I should get something right around 1.36. And again, very close, within 2 significant figures. And why is it not exact? Because we rounded. If we had exact values in here, we'd be even closer. But you can see, once again, we're very, very close to 1.36, just shy of 1.35 here. We could try it with one more value just to sort of show the concept again. So this time I'll use this value here of 0.167. Or actually, let's make it interesting. Let's do the negative one. So I'm going to take negative 2.53 and take that to the third power, minus 5 times negative 2.53, and that should all be equal to negative 2.53 minus 1. Once again, I can do the right-hand side without a calculator. I already have a negative 2.53. I'm taking away one more, so it'll be negative 3.53. Once again, these were rounded values, so I'm not expecting to get exactly the same thing, but I should get very close to it. So I take my negative 2.53, taking it to the third power, minus 5 times negative 2.53. Close my parentheses. I press enter, and again, I'm expecting to get something around negative 3.53 and negative 3.54. Again, only 1/100th off, and that was just because we had rounded earlier. So we are finding values that make these true statements. And again, what were our techniques? We took the left-hand side of the equation, put it into y1, put the right-hand side into y2, used our second trace for intersect, and found those values of x. All right, until next time.